Okay, hello everybody. Today we will discuss the Faraday's law. You know that from the experiments of Faraday's, when a flux of magnetic field through some loops is changing, then in the loop will occur the EMF E equal to minus d phi of B over dt. E is a electromotive force, and when in the loop we have the resistance of R, then you will have the induced current IC is E over R. I will show you how we can explain this minus sign in the formula here. To understand this minus sign, you have to use the Lenz's law. It states that when, for example, d phi here is positive, then the electromotive force will be negative and vice versa. So, for example, I prepare here a loop for you to practice that. Imagine that we have the loop here or the loop here. The loop is put in a magnetic field of B, right? This is vertical. Now when the phi of this magnetic field through this loop is, let's say, increasing, or here another one, phi B is decreasing, then what is the direction of this induced current in the two loops here? For the first one, you will know that when B here is bigger, then the phi B is increasing. So with the minus sign here, the induced current will be created in the loop so that it will create another magnetic field that is opposed with the original one. So this is called, let's say, B prime. Then we use our right hand rule to determine the direction of this current. You put your right hand rule this way, but your thumb will follow the direction of the B prime. Then you will easily see that the direction of the IC will be this way. Correctly? Okay, this side is in front of you. For this case, the current will create another B. This is B prime. Then when you use your right hand with your thumbs up, you will find that the IC has this direction. Okay? So this is how we implement this minus sign in the real situation. Now I would like to talk about the Maxwell Ampere's law. You will see that from the Ampere's law, you have the line integral of B ds is equal to mu 0 multiplied with the current. But for the changing or varying electric field, Maxwell expand this normal current with another one. He called that is the displacement current. So we get the new equation like the integral of BDS here will be the normal current plus the term for the displacement current. This is d phi e over dt. You will see here in this term we have the flux of the electric field through some area, and when we don't have the normal current here, the current by the motion of charge like free electron in the conductor. When we don't have that, then when we have the changing electric field, we also have the magnetic field. So in other words, we can say that, okay, when we have the changing electric field, we have magnetic field. So when you compare this derivative with this derivative, you will see the similarity between the two, right? But the difference here is this side. We have here the plus side, here will be the minus side. So how can we implement that in, for example, in the previous example here? So let's say now I have the line, the closed line, in which I will calculate this integral. Then the existing electric field is here. Another one, I take another loop with the electric field. Then in this case, the flux of this electric field is increasing, and for this one, the flux is decreasing. So what happened with the magnetic field created by the changing electric field in the two cases? First of all, when the phi is increasing, then the current has the same direction with the existing E. So I draw the E. This the current, we call it the displacement current, ID. Then similar to the magnetic field created by some current, we use our right hand rule and we will determine the electric field at this position. This is the electric field created by the increasing, this is the magnetic field created by the increasing electric field. Or for example, at this point, you will have the B, like this one. Okay, for this one, because phi E is decreasing, so the displacement current is downwards, then we can use our right hand rule to determine the magnetic field. So in this case, you will have the magnetic field at this point is outward, and at this point is into the board. Now I have an example for you. This is the problem number 13 in your book. We have here a loop of wire of the shape of the rectangle. We have here the loop with the shape of a rectangle with the length L and the width W. This loop is close to a straight line with the current I from the left to the right, and the distance between the line and the loop here is h. Okay. The first question is A. determine the flux of the magnetic field created by this current through the loop. B. Suppose that the current here varies with the time with the function a plus bt, where a and b are constants. The question is, what is the direction of the induced current in the loop? And the question C, determine the flux when the flux is changed. So what is the magnitude of the current IC? Is this clear? Okay, so now I will start with the solution. Here is the solution. First of all, we have to calculate the flux through this loop. It's not easy because you know when B is constant, then it's easy. You can use the definition of phi B is B multiplied with the area A with the loop here, multiplied with the cosine of the angle made up the B vector and the normal vector of the area. But in this case, you will see that the magnetic field is stronger when the point is close to the current. But when you go away from the current, B will be weaker. So this is our problem. So we have to calculate the phi, like the integral of d phi, and this is d phi b, and this is the integral of b dA without the cosine, because now you will see that when we use our right hand rule, we put our thumb through this current, then you will see that in the loop here, the B will be into the page, right? Let's check it. And at this side, it will be out of the page. Okay. So the problem is now B isn't constant. We all know that the B is mu 0 I over 2 pi d. With d, the distance from the point, for example, I calculate the B at this point, then d is the distance from here to here, right? Remember that? Okay, so d is increases, right? Then B decreases. So now, to make it easy to calculate that, so I now assign a x-axis through this. This is the vertical one, and here is the origin of the x-axis. Now, I had to determine the dA. The dA is very tiny area, and I define the dA this way. Okay, so this is our dA. The height of that, of course, is dx, right? And with the length. So in this case, I have dA is L multiplied with dx. Okay, so instead of d here, I will use the instead of 2 pi x instead of d. Okay, then you will see that the phi will be the integral of b L dx, and I substitute the value of b here, so I have the integral of mu 0 I over 2 pi x with L, then dx. But you have to determine the range for this integral. You will see that when we go along this x-axis, we will start from this point to this point to cover all of the area of the loop. So here, the first point here has the coordinate of h, right? H. And this point has the coordinate of x plus w, right? So here I copy it here. So it's easy for you to calculate this integral. Then we will have the phi b. In this case, I take all of the constant out of the integral. I have here mu 0 I L over 2 pi, right? And here the integral of dx over x is a logarithm of x with the range from h to h plus w. And it's easy, right? So this is mu 0 I L over 2 pi, and the logarithm of h plus w over h. That is the final answer for the first question. Okay, so we have had the first answer for the question A. The phi b is mu 0 I L over 2 pi logarithm of h plus w over h. Now, this is the case in which I is a constant, or when we have the DC, direct current. But now for the question B, I is a function of time. So what happened? We have here the current I is A plus BT. This is the linear function of time, right? Then the phi B isn't constant anymore. So in this case, we have to determine if the phi B through this area increased or decreased. You see that over the time, with AB is constant and it is positive, then I will be bigger with the time. So the result of that is B will increase or the phi B increase. In this case, apply the Faraday's law to the situation here. You will see that because phi B increases, then the induced current occurs in this loop will have the direction so that the magnetic field created by this current will have the opposite direction with the B, right? So the B prime will be out of the page. Then you will use your right hand to determine the current. So this is the induced current. So for the question C, we say that the induced current will have the direction anti-clockwise, right? Or counter-clockwise. This is the answer for the question B. Now, for the question C, what is the magnitude of the IC? So I have here IC is, when we take the magnitude of that, then let's see the derivative of the d phi over dt here. This is the EMF multiplied with the reverse of R when we have the resistance of the loop. So let's calculate this one. This is phi b, sorry. So with the phi b, we have to write phi b now will be mu 0 L over 2 pi, the term here with the logarithmic of h plus w, then over h multiplied with a plus b t for the current. Okay, so when we take the derivative of that, you will have here the b only, a will be 0, and here so d phi b over dt will be mu 0 L over 2 pi logarithm of h plus w over h and multiply with b only. Okay, then we can easily find the induced current will be the EMF here over R. So the result will be, sorry, this is an L, not I, over 2 pi R, and I put the B here over H. So this is the magnitude of the induced current. That's all. Thank you.